are worse in terms of clouds. As you get closer to the Great Lakes, in the wintertime, the Great Lakes dump a whole boatload of snow on Lake Buffalo and Rochester. But around April, the lake is warm and it tends to keep the clouds away. So there's only again, about a 5% worse chance in upstate New York. And once you get off of upstate New York and you get into Vermont and New Hampshire and Maine, then the chance of clouds is really high.
Okay, guys, started the YouTube session, so it's being streamed live to YouTube now.
I'm here.
All right, guys, we're going live.
Welcome, everyone. Hey, we made it to the Griffith. All right, so welcome to our March general meeting. I'd like to point out that next month in April, we will not be having a general meeting because of the eclipse, but we will be having a general meeting in May for a show and tell of all of the fantastic eclipse images we expect to see from you guys and ladies. So, so there's that. We also, President Daryl is not here tonight. He's recovering still, but we send him our well wishes and speedy recovery for that. The other thing that we wanted to go over was that we have raffle tickets. Does everyone have raffle tickets? Yes? Okay. And online, for those who are tuning in to Zoom, Spencer will be dropping a link for you to use so you can submit and be submitted for a possible draw in the raffle tonight. We have some fantastic prizes. Missing. Oh, it's on the other side. Okay. It's all there. Okay. We have fantastic prizes tonight. And so let's get started first with our speaker. It is no other but Tim Thompson, our President Emeritus, who's going to be giving us a guided tour of the universe. He is our local physicist and astronomer. He's worked at JPL for God knows how long. Oh, do you want me to go over that too? Okay, I'll do upcoming events. The upcoming events, if I can get the thing to work. Nope.
What are you looking for?
I'm looking for the slides. Okay, I'll just go over it. All right, so we have a star party this Saturday from 2:30 to 9:30 p.m. We have also elementary school star party coming up for outreach. There's 3 of those. Is it showing? Let me see. Oh, thank you. Yeah, I'm trying to pull up the... There we go. All right, so we have the Community Magnet Charter School on March 14th. We have Robert Frost Middle School on March 15th. You can log into the Night Sky Network for further details. We're also selling 2024 calendars still. They're still available. They're now $15. We also have LAS jackets available, sizes small to extra large. There's something.
Tim's microphone, because we heard you blowing your nose through Zoom.
Oh, this is fantastic. Okay. Very pleased though.
Okay, so try talking on that one.
Where do I speak? From the beginning? bear with me. Oh, sorry. All right, so yeah, it's good practice. All right, so we have a star party at Griffith Observatory this Saturday from 2:30 to 9:30 p.m. It's exciting. We're going to be all spread on the lawn. Bring your telescopes, bring merchandise, bring your friends, bring your family. We also have... I need your face. We also have Charter Middle School on March 14th. Yeah, March 14th, yeah. And the Robert Frost Middle School on March 15th. We have LAS jackets for sale from small to extra large. We are also selling the 2024 calendar still for $15 instead now. And we're going to be starting a new astrophotography contest for our 2025 calendars with prizes for those winners. So look forward to getting an email blast about that coming up. So without further ado, let me introduce our guest speaker for tonight, Tim Thompson, President Emeritus, physicist, astronomer, JPL retiree, talking about a guided tour of the universe.
Well, it's not quite as pretentious, I suppose, as a brief history of time, but it is a guided tour of everything, the whole universe. And so we might as well start close to home with the sun. And if you've ever wondered how big the sun is, that little dot up there on the upper left, that's the Earth compared to the sun. Real size, real scale. So. And this is an H-alpha image by Alan Friedman. If you people are solar observers, H-alpha people, you should look up Alan Friedman if you don't already know him, because he's a great imager. There's all kinds of stuff on there, and maybe I'll talk about it, and maybe not. They call it the solar system for a reason, because it consists of the sun, a bunch of junk. And so you can see here over 99% of the mass of the solar system is the sun. The big takeaway from here is you'll notice that the sun is bigger than like 95% of the stars in the galaxy and probably in the universe. So don't let anybody tell you the sun is an average star. They always say that the sun is not. No, the sun is not an average star. It's big. So you don't need to have an inferiority complex about coming from some wimpy star, some average star, no, big star. And the solar system consists of the sun, the planets, and almost all the planets are the Jupiter, and then other stuff left over. And of course, asteroids, comets, all that stuff. It's just junk laying around in the solar system that the sun could do without just fine. So, and remember, the talk is being recorded, so if I go through it a little bit fast, you can always go to the YouTube channel after the meeting and scroll through it and freeze the frame and read everything and study it, because I am, of course, a fantastic speaker and you'll want to do that. But here's a plot of the solar system mapped out for you. Upper left is the inner planets out to Jupiter. The numbers that I have there in the upper right of the upper left quadrant are the closest Jupiter ever gets to the sun is perihelion distance, the average distance, and the farthest distance, and then down on the bottom is the period in years, and those distances are in astronomical units, which is basically the average Earth-Sun distance. So you see that Jupiter hangs out about 5 times farther from the sun than the Earth does, takes almost 12 years to go around once. If you look over in the upper right quadrant, you see Pluto takes 247 years, almost 248 years, and gets as far out as 48 astronomical units from the sun. And so it's pretty far out there. When we say solar system, almost always, that's what we're talking about. People just mean that little clump of planets, and that's the solar system to everybody. You go outside that, you're outside the solar system, and that happens to be spectacularly untrue. If you look in the lower right quadrant, you can see Sedna, which is one of those beyond the Kuiper Belt objects that is gravitationally bound to the sun, but it's in an 11,000-year orbit, and the closest it ever gets is 76 astronomical units, well beyond Pluto. And it will do that around the year, say, 2075, 2076, say about 50 years from now. Saturn will reach perihelion. I don't think I'm going to be around 50 years from now, but some of you might be around 50 years from now. And it goes way out to 937 astronomical units. And the solar system is surrounded by a shell of stuff, long period comets, called the Oort cloud, named after Jan Oort. And the inner extent of that cloud is thought to be about 10,000 AU out, and that's the lower left panel. That's 55 light days away. It takes light 55 days to get out there, or distance from the sun are a little over 300,000, 360,500 years. That is a long, but gravity actually holds on to things that are like up to 1.6 light years from the sun, about 100,000 astronomical units. So the sun's gravitational reach is actually quite far. Out that far away, the orbital period is around 11 million years. And that's where this period comets eventually get down to us. So the solar system is actually quite big. The sun's gravitational reach is quite far. But we will come back to the planets for a few minutes because that's where we hang out, and that's the interesting part of the solar system. These are all various Voyager spacecraft or other spacecraft images of the planets. You can see the Earth down there. The numbers that you see here, the top number is the diameter of the planet in terms of Earth diameters, and the bottom number is the mass of the planet, or its weight in terms of Earth masses. You see Venus is almost as big as the Earth, and that hot orange color is just made up because this is a radar image, and radar doesn't have color you can't see. Make it whatever color you like. The other planet colors are pretty much real color, which your eyeballs would see. And there's Mars, about half the size of the Earth. Here's the Earth, and there's the Moon. The Moon is quite large compared to a quarter of the size of the Earth in diameter, but very much less in mass. The size is to scale in this image. That's how big the Moon is compared to Earth. The distance, however, is not. If the Moon ever got that close to the Earth, somebody would be in for a very bad day. But despite rumors to the contrary, we have actually been to the Moon. People went there. Apollo 11 launched in 1969, 11 through 17 went to the Moon, except Apollo 13, which had a little bit of a problem. They just kind of swung around the Moon, came back to Earth. So people have been to the Moon, and rumor has it that someday soon people will go back to the Moon in grand style, I hope, but we'll find out if that's true. Meanwhile, here on the upper left is Neil Armstrong stepping onto the Moon. So the lunar excursion module that landed on the Moon had a little television camera that kind of flipped out like an old ironing board and then looked at the ladder so we could get images of Neil Armstrong stepping on the Moon. That sent a television signal back to Earth that could not be received where it was supposed to be received, so it was received in a backup station, and that television signal was projected onto a television screen so you could sit there and watch it, and a television camera looked at the television screen, and that's the image you see here, is a television camera looking at a television screen, and that's why it's all grainy and screwed up. The original signal was recorded on magnetic tape and then erased by accident by people who wanted to recycle the tapes that were not marked extremely important. So the original signals are all gone. The only signal we're ever going to have is the one from the television camera looking at a television screen. And it makes it look kind of, that might be actually pretty cool. The Apollo up in the upper right corner, 3 guys squeeze into this little thing. About a decade ago, I tutored a 13-year-old girl from Beverly Hills whose mother paid me way more money than she needed to, but I didn't complain. It was obvious from the beginning that she thought the Apollo astronauts went to the Moon in the space shuttle. She had no idea there was an Apollo capsule, and I showed it to her. Like, they went in. That's right. They squeezed 3 little guys into that thing, and away they went to the Moon. And the bottom images are a lunar reconnaissance mission images of the Apollo 11 and Apollo 17 landing sites. And we can see boot tracks and all kinds of real neat artifacts, one being a laser ranging retroreflector, and I'm going to get into that in just a minute. But first, I want to draw your attention to the middle image on top, which is the Saturn V rocket that launched people to the moon. You know, the little red dot on top is the Apollo capsule, and all that is what you need to get that Apollo capsule off the Earth. And the reason for that is that you know how much energy you need for the Apollo capsule. So you put the Apollo capsule and you put a gas tank under it and you fill the gas tank with rocket fuel and you light it off and it goes up and then it crashes because you've done the thing. Now it can't lift itself. So you need to add more fuel to lift the fuel that lifts the Apollo capsule. But and it won't work. So you have to add more fuel to lift the fuel that lifts the fuel that lifts the Apollo capsule. And that process iterates several times where you have to have the fuel to lift the fuel to lift the fuel to lift the fuel. And before you know it, you've got a Saturn V rocket and that great big huge thing. So just keep that in mind when they talk about sending people to Mars, which is a lot farther away than the moon. And you're going to need a bigger thing than a little Apollo capsule, and you're going to need fuel to lift the fuel to lift the fuel, and it's going to be an issue. Now, the retroreflector that was left behind by the Apollo astronauts, here's one on the right from the Apollo 15 site. This is a really interesting doodad because as long as your angle of incidence for the light you shine on it isn't too low, instead of reflecting the way you would expect it to reflect, go down and bounce off, the angle of incidence and the angle of reflection are the same. That's not how it works. It bounces light straight back the way it came, no matter what direction it came from. And that's really handy because we can shine a laser from the Earth to the moon, and for every 100,000 trillion photons of light the laser sends, one makes it back to Earth. And that's enough to measure the moon receding from the Earth at about 1.5 inches per year, 3.82 centimeters. So the moon is drifting away, which means its angular size is getting smaller. And that means in about 563 million years, according to the last NASA computation, there will be solar eclipses because the moon will be too small to cover the sun and you'll get only annular eclipses. So you got to go and see the eclipse next month because in 63 million years there won't be any more. And so this is your last chance, right, to catch the story. So there you are. So I do want to talk about a couple of things that get press in the solar system. Mars gets a lot of press. Here the sizes are not to scale. Phobos and Deimos are tiny little rocks. Their diameters are given under their names. They're minuscule compared to Mars or practically anything else in the solar system. But Mars gets a lot of press. And one of the reasons Mars gets a lot of press is because the Martians have been trying to conquer us for like centuries, and they screw it up every time. They are the most incompetent planet conquerors probably in the universe. And so they get a lot of press. But aside from the fact that they can't conquer anybody, Mars also gets a lot of press because it's a small planet with big things on it, really big things, like Valles Marineris, the Mariner Valley, which is almost as long as the US of A, as you can see on this diagram. It's about 10 times longer than the Grand Canyon and like 5 times wider. And you can follow it from like Nevada to Georgia based on this map. And that's because the surface of Mars is not like the surface of the Earth. Earth's surface is broken up into plates and they move around and go under each other and make earthquakes and do all kinds of stuff and erase surface features. A big thing on the surface will eventually get subducted and melted and recycled. On Mars, that doesn't happen. No plate tectonics. So if you have something hot under the crust, it just works forever. You break the crust and it just keeps breaking and breaking. So not only do you have really huge valleys and canyons like this, you have really huge volcanoes like Olympus Mons, which is basically as big as France, as you can see. Here there's a hot spot under the crust, a mantle plume, hot magma coming up, punches a hole, makes a volcano, and it just keeps going in one spot because nothing's moving around. The plates aren't doing anything, then you get a great big volcano. Now, Mars might not be able to conquer us, but we've been working on Mars and doing it with rovers, a number of rovers. The little Sojourner rover in the lower left, it was the first one that ran around for, how long did, 83 sols. So you see a sol is a day on Mars, which is like 24 hours and 40 minutes, whereas the Earth is like 24 hours. So a Mars day is a bit longer than an Earth day, which means if you work at JPL and you work on a Mars rover crew, you need to work on a Mars time schedule, not an Earth time schedule. So your shifts are Mars shifts, not Earth shifts. So if you're driving the rover, you may have to go into work at midnight to drive the rover because that's daylight on Mars, and that's just the way it is. And we've gotten some pretty big rovers up there, and we've done lots of spectacular work. But in the last Perseverance rover had a helicopter along with it. And so here's the Ingenuity helicopter with its counter-rotating blades. It's really hard to fly a helicopter on Mars. It's not an easy thing to do. The original plan was to fly it minimum 5 times to prove of the concept that you could actually do it. It actually flew 72 times for a total of a little over 2 hours of flight time and 10 miles, and was actually used to scout around the rover. So, well, what's interesting around here? And then they could know where they want to send the rover. But the Ingenuity has a cracked blade, and they can't fly it anymore. It'll come apart, so it's going to sit there on Mars without flying anymore fairly soon. And so is a picture of what Mars looks like to the Curiosity rover. You can imagine going someplace on Earth, maybe Amboy Crater, that somebody's going to this weekend, I don't know, that looks kind of like this, except if you look at this really see there's not a blade of grass or moss or anything in this image, so there's nothing else but dirt. But it's got geology. It looks kind of like Earth. So if you're going to send people to Mars, send a geologist with a rock hammer. They can't do what geologists do on Earth, take off their shirt and get sunburned while they're pounding on the rocks, but it's still, they can pound on the rocks and find out what's going on. There's weather on Mars. There is an atmosphere. The pressure sensor on, I think it was the Curiosity, yes, the Curiosity rover had a pressure sensor on, and you can see that in the upper left, 6.9 to 7.8 millibars. Don't worry what a millibar is. All you really need to know is that the standard air pressure where we are on the surface of the Earth is 1013.25 of those millibars. So as you might guess, if you only have 7 of them, you don't have much in the way of air or air pressure. And so flying a helicopter in that kind of almost not there air is really hard to do. That's why the Ingenuity helicopter was such a fantastic thing to pull off, because there's almost nothing to fly in. You have to go up 12.5 miles in our atmosphere into the stratosphere to find air that thin, if you can call it air, because if you take off your helmet and breathe, and it's over. So if you look at the temperature sensor on the lower right, that's not bad. The high temperature during the day was 37 degrees Fahrenheit. The low air temperature at night is minus 103. These are temperatures typical of polar regions of Earth. Wintering over in Antarctica, you run into 120 degrees below zero, colder than this. And during the summer, you can probably push the temperature up to about 37 degrees Fahrenheit down in Antarctica. So we're used to working with temperatures like this. We're used to working with a little more air around us, but we're used to working with temperatures like this. So if we send people to Mars, we can probably handle that problem. Now, aside from Mars, one other thing that gets press is the rings of Saturn, the true Lord of the Rings. I really like Saturn and its rings because when I was a little kid, I lived across the street from my elementary school, and I would walk home for lunch. And I would watch Sheriff John's cartoons during lunch every day, and I would watch Colonel Bleat race around the rings of Saturn in his little race car, and I thought it was great. Turns out you can't do that because the rings of Saturn are not solid, but I was a little kid and didn't know it at the time. Saturn's rings are great. Now remember, the solar system is made up of the sun, the planets, and a tiny 0.01% junk left over. Amongst that junk is comets. And I know some of you who are comet observers out there in the audience may be offended by the notion that you're looking at junk, but that's pretty much what it is in the context of the solar system, just a bunch of junk laying around. And so there's several comets. The comet Hyakutake, which is center top, and also on the lower right. The lower right image, you'll notice you can compare it to the Big Dipper. And I went out, Lockwood, and looked at it with my eyeballs, and it stretched across the sky like this. It was incredible. You'll never see another comet like that. Glad I was around to see it. And the image in the center bottom was made by the Giotto spacecraft, the European Space Agency. Everybody sent a spaceship to look at Halley's Comet when it came through in 1986, except the United States. And here the sun is shining on the comet, heating up the surface. The water underneath sublimates into a vapor, breaks the surface, and comes spewing out and inhales comet dust and other stuff with it. And that's where the comet tails are born and how they're born. And there are a bunch of comets that swing around by the sun, some of which swing in and don't come back out. Aside from comets, there are also asteroids. Cleopatra in the upper right is a near-Earth asteroid, and so those are radar images. As they came by the Earth, the NASA radar at Goldstone, the Deep Space Communications Center, just bounced radar off of it as it tumbled, and so these are all images made of Cleopatra as it tumbled. I call it the dog bone asteroid. Ceres is now a dwarf planet like Pluto, but it's still an asteroid in the main asteroid belt, and I think something like half, or maybe more than half, of the mass of the million asteroids in the asteroid belts is Ceres, and the rest is everything else. And Gaspra and Ida asteroids and spacecraft have flown by. Ida is 35 miles from end to end, which is about the distance from JPL to Long Beach. So that asteroid would fit right on top of LA Basin. If it landed on top of LA Basin, that would be tragic, I'm afraid. Now remember the part about leaving the solar system. The Voyager spacecraft, I checked these this morning, so these numbers are accurate as of this morning. Voyager 1 is 162.885 astronomical units from the sun. Voyager 2 is only 135.981. And New Horizons, which flew past Pluto in 2014, I think it was, is only about 58 AU away. The Pioneer spacecraft are silent. They went silent long ago. Somebody's sure where they are. You could make up a number, but I didn't bother. The elapsed mission time for the Voyager spacecraft is over 46 years. And the bottom time that I have there, like for Voyager 1, is 22 hours, 34 minutes, 12 seconds. That's the one-way light travel time from here to the spacecraft. So if you pick up your radio and you say, "Hello, Voyager," 22 hours later, Voyager hears you and says, "Hello, Earth," and 22 hours later you hear it. So you say, "Hello, Voyager," and 44 hours later you hear Voyager say hello back. So if you want to command the spacecraft, you send a signal and it sends a checksum back. It's a little code that you make up out of the signal that tells you if it received the signal that you sent. It's a long way. Things can get garbled in transmission. So you can look and see, did it actually get what I sent? And if it didn't, you have to send it again. And it's a 44-hour round trip to figure that out. So you need to know well in advance what you're going to tell it to do in case you have to tell it again to do the same thing, because it's a long ways away. The Voyager 2 spacecraft is functioning properly. Voyager 1 is not. Voyager 1 stopped sending science data back to Earth in December. It has a communications problem inside its own electronics. No one is altogether sure what it is that's wrong, but it's sending back garbled stuff instead of science data. But we can ping it and get the signal and see where it is and where it's going. But at the moment, it's not working right, and they're trying to patch it. So we may have lost Voyager 1 as a source of science information. Voyager 2 is still working. Now, the sun dominates the solar system, but is a star in a universe of stars. And as I talk about this, I want to bring up an interesting coincidence that I ran into. I should have known it a long time ago, but for some reason it wasn't until recently I realized it. The number of inches in a mile is very close to the number of astronomical units in a light year. They're almost the same, very close to each other, which means if you make a scale model of the solar system with 1 inch per astronomical unit, and you know Pluto only gets 48 astronomical units from the sun, 48 inches is 4 feet, you can lay out a model like that on a table. You can lay it out on the floor. If you're in a classroom, you can just lay it out on the, it's easy. And if you have a 4-foot kid, you can just lay him down and put the sun at his head and Pluto at his feet or whatever. And there's your model of the solar system. But on that scale, 1 light year is 1 mile. So the nearest star to our sun, Proxima Centauri, is 4.243 light years away, which means you have to go 4.243 miles from our 4-foot kid's head to get to the next star. And that's a really great way of convincing people that space really is mostly pretty empty. There's not a whole lot there, and the stars are not really close together. Our little piece of the universe is way far away from the rest. But here in the lower right is a picture of Proxima Centauri. It's this tiny little red dwarf star. It's often said in our own solar system that Jupiter is a failed star. It is, but you have to understand that Jupiter didn't just fail, it failed miserably. It's not almost a star. It's way short of being a star. The smallest, tiniest star you can get is about 80 times more massive than Jupiter. So there's a lot of room. Jupiter failed big. So don't let anybody get away with telling you it used to be a double star system. I know people who think that Jupiter used to be a star and now it's not a star anymore. They're weird people, but no. 1 star, all we ever had, all we're going to get. So stars, like people, like to hang out together, like we're hanging out here, and those other people out there in Zoom land think they're hanging out with each other because they can see little faces on their computer, but they're not. We are hanging out together here in this room, and they're just kind of voyeurs looking through the Zoom window. All you guys on Zoom, be here next time in May, right? To be here. Okay, so except for the furry face in Denver, okay, but we'll let you off the hook. So here's the Pleiades open cluster. Subaru in Japanese, if you own a Subaru car, the emblem on your car is a stylized version of this cluster. It's a Pleiades open cluster. So maybe 1,000 stars or so, and they're fairly young and they're bright blue, and there's some dust hanging around, but that's just passing in the night. The dust has nothing to do with the formation of the stars. We call it an open cluster, and there are a lot of them. Sometimes they call them galactic clusters, because as you can see in the image, there's a lot of room between the stars. They're not really crowded together. Clusters like this are always fairly small, maybe 1,000 stars, a few thousand, or a few hundred stars. If you look it up on Wikipedia, it will tell you it's 16 light years across. You can look at this picture and say, okay, 16 light years, which way? This way, that way, this way? Then nobody tells you, right? So you just draw a circle around it where you think a circle would fit, and okay, it's 16 light. Nobody knows how far across it is. And also when you look at this picture, remember there's 3 dimensions here. So the cluster, the bright stars of the cluster are hanging out in front here, and those rest of those stars are way back in the background here. There's depth in the picture. So there's a lot of open clusters like this. They go around the spiral arms of the galaxy, and they're subjected to torque effects, and they eventually get torn apart, and the stars just kind of drift off and become field stars in the galaxy. Aside from little clusters like that, there are also big clusters. Here is an image of Omega Centauri, which is the largest globular cluster in the Milky Way system. And you can see it from here, but you have to be in a spot that has a really good southern horizon. As I recall, if you're in Lockwood Valley, there's a little notch in the mountains, and Omega Centauri moves through the notch. If you know exactly when it's moving through the notch, you can look and see it. It skims the horizon from where we are, but it is actually visible if you got a good horizon. So go to the southern hemisphere and look straight up at it. This is a really big one, maybe 10 million stars, hard to say, 4 or 5 million solar masses. This is not a typical globular cluster where all the stars formed together. This is surely the core, remnant core of a dwarf galaxy that was gobbled up by the Milky Way, which gobbles up dwarf galaxies galore, and this is all that's left. The rest of the galaxy has been digested into the Milky Way and it's gone. And there are a few other globular clusters that have suffered the same fate. So we have little open clusters with a lot of room. We have globular clusters with lots of stars. You can see they're fairly well packed. And of course, it's much bigger. The open cluster was, 20 light years across. This is 150 light years across. And in this case, globular cluster, okay, you can kind of, figure out roughly how big it is. It's not as bad as an open cluster. But stars also come in just a great big huge cloud of stars, because we're looking at the Milky Way galaxy from the inside. This image is Messier object number 24, and it's a common mistake to label the open cluster down in the lower left corner of this image as Messier object 24, but it is not. That is NGC 6603. This whole star field is M24, which Charles Messier described as kind of a cloudy thing or cloud of stars. I think he could tell it was made out of stars, but barely so. Then if you look at this image, you'll notice the stars to the right, and especially kind of the upper right and far right, have a kind of a yellow color to them. But if you look across the image, you'll see that the stars pick up a bluer cast. And so if you look in the lower left, the background stars look pretty blue. So there's a gradient of color in the images. And that's because of the difference in color between low-mass stars near the center of the galaxy, which is in Sagittarius, and the higher-mass stars in the spiral arms. And we will see examples of that in a few minutes. So stars like to hang out in huge clouds, big clusters, little clusters. Stars also have a life cycle, and stars like the sun end up as what we call planetary nebula. So if you look at A Bell 39, center image bottom, it's nice and round and nice and blue, and that's a good example of why they're called planetary nebula. Because when the old-time astronomers looked with their old-time telescopes, what they saw was round, like a planet, and fuzzy like a nebula, so they called them planetary nebula. Doesn't have anything to do with planets in them. They just called them that because of their round shape. And the cat's eye, just in the lower left corner, would look around in an old-timey telescope, but now with the Hubble Space Telescope, which took all these images, we can see there's a lot more stuff going on in there. Likewise, the Helix Nebula on the upper left. All of those things you can see might look round in an old telescope, but it's pretty hard to imagine that the Ant Nebula on the upper right or the Hourglass Nebula on the lower right would ever look round in any telescope unless you need to fix the optics. But we still call them planetary nebula because that's what we call them for historical reasons. And you have to remember that astronomers are amongst the world champions of the old saying, if it ain't broke, don't fix it. The magnitude scale we use for the brightness of stars is over 2,000 years old, but we still use it because it works, and so why not? So these planetary nebula, the star probably loses about half its mass. Sun will give up half its mass into the interstellar medium and replenish the dust that we saw, like in the previous image. Here, the dark lanes in this image, like in lower right especially, it's not an absence of stars, it's dust. It's opaque clouds blocking your view. So you only see what's on our side of it, go around it, see lots of stars in the background, because they're on the other side. These stars are formed in the dust cloud, and then they return half of their guts to the dust cloud. So from dust to dust, as they say, well, that works great for stars. Stars like the sun go out as planetary nebula in relatively calm style. In about 4 billion years, the sun will do that and gobble up the Earth in the process, so we need to go find a safe place on Mars or the moons of Jupiter or something, because the Earth is doomed. Sorry about that. But larger stars, say more than maybe 8 solar masses, are too big to do that. They can't go out calm, cool, and collected. They go out in a bang, a real bang. And so the Crab Nebula, Messier object number 1, supernova 1054, this is a supernova remnant of a core collapse supernova that blew up around about 10 July 1054 and was visible, the remnant was visible in the daytime sky for almost 2 years. It was very nearby, very bright, but not near enough to do us any harm. If you set up a supernova close enough to the Earth, that could be a problem, but they're all too far away. There's a pulsar in here that pulses 30 times a second in visible light. We can measure the expansion velocity. And just for you conspiracy theorists, this went off 10 July 1054. On 16 July, about a week later, the bishops of Constantinople and Rome excommunicated each other, which caused what they call the Great Schism of 1054, which split Western and Eastern Orthodox Christianity from each other. Was this a harbinger 10 days before? I don't know. I will leave you to think about that. But hey, coincidences do happen. So all that dust and junk in the universe, here's one of my favorite pictures of an example of that. Pretty close to dead center of the image is the Horsehead Nebula. And you can see the horse head. It looks like the horse has turned its head towards us a little bit. But as one enterprising Boy Scout actually pointed out to me, you can see the tail of the horse. So it's named after the wrong end of the horse's anatomy. But it's named the Horsehead Nebula, and we're stuck with that. So upper center of this image is a very bright star. It's and surrounded by a bunch of other bright stars. And this is the Sigma Orionis cluster, a tight little cluster, very, very hot, very bright stars that emit lots and lots of ultraviolet radiation that impacts the dust cloud that inhabits the bottom half of this image. You can see that in the bottom half there are a lot fewer stars than there are at the top half, because you can see over it and see the distant stars while you're just looking at the stars on our side in the bottom half. And as the ultraviolet impinges on the dust, it breaks up the dust clouds, smashes into them, and liberates hydrogen gas from the ices on the dust grains. And the red curtain of glow that you see above the dust cloud is hydrogen alpha emission. It's hydrogen released. So you're seeing the stars, the gas, the heavy dust. Where the dust is thickest, it wears away slower. Where it's thinner, it wears away a little quicker. And there are several stars embedded in the dust cloud. The Flame Nebula, the really bright one on the lower left, is a cluster of stars actually embedded in the dust cloud from which they formed. And the really bright star right next to it is Alnitak, which is the leftmost star in the belt of Orion, if you're looking at Orion in the southern sky. So this is in Orion, and the Horsehead Nebula is really hard to see in amateur telescopes. It's not like Orion Nebula. M42 is easy. You see that naked eye. Horsehead is a tough one to spot. So if you go out to dark sky, try the Horsehead someday. So all this stuff, the dust clouds, the stars, the gas, make up a galaxy. And here is our Milky Way galaxy on the road to wherever. Our galaxy is a spiral galaxy, and there's a diagram here that kind of shows you what an edge-on spiral galaxy typically looks like. A bulge in the center of mostly old low-mass yellow stars, and the spiral arms with blue stars. You can see the color difference in the diagram on the right, and you can see some of that color difference as well in the Milky Way image on the left. standard answer for how big is the Milky Way is 100,000 light years. That's probably too small. 120,000 is a better image, and recent research shows it's probably close to 200,000 light years across. But 100,000 is good enough for now. So our problem, of course, is that we are inside the Milky Way, as evidenced by the image on the left. It's a lot easier to see what a galaxy looks like if you're outside and you can turn around and look at it. Well, there it is. But if you're inside of anything, how do you look that way through it and tell, okay, that's where the edge is? Well, maybe the edge is there. Maybe the edge, how do you know where the edge is if you're inside? Well, you can do it, but it takes a lot of work. And so this image, which originally published in 2008 using Spitzer Space Science data, and the project, I helped these people in Wisconsin for a while, is the Galactic Legacy Infrared Mid-Plane Survey Extraordinaire. And you will notice that the acronym spells the word glimpse. Now, you can't have a project in NASA without an acronym, and you score extra points if you make it a word that you can actually pronounce. And in this case, they scored a lot of extra points because glimpse, and they're looking at the galaxy. It turned out really well. The Magellan spacecraft that did the radar images of Venus was originally the Venus Orbiting Imaging Radar, VOIR, which is the infinitive of the French verb to see, and is perfect, but they renamed it after Magellan for no particularly good reason and ruined a really good day. I was very mad at them when they did that. So this is an image of what we think the Milky Way looks like based on our infrared data, optical data, radio data, all that. Maybe 100,000, 200,000 light years across. And if you haven't noticed, there we are, about halfway, maybe a little less than halfway, between the edge of the galaxy and the core, which has a small bar. It actually has two bars. Our galaxy, you can get dunked twice at the center of the galaxy, right, because it actually has two bars crossing over each other. We're not in one of the big spiral arms. We're in one of this little thing called Orion Spur. And you notice the rotation periods in the text on the right. It takes 250 million years for the sun to go around the galaxy once. But the spiral arms are not structures of stars moving, where all the stars move in step with each other like soldiers marching along. No, they are waves of star formation, density waves propagating through the plane of the galaxy. They move much faster. The spiral arms only take about 50 million years. So from the point of view of the sun, where we are, relative to us, what we see is the spiral arms moving over us like this. And when that happens, the galactic gravitational tide changes. And remember that the Oort cloud is way out there at the edge of the sun's ability to hang on to things with gravity. So the gravitational tides could kick Oort cloud comets and send them in and cause mass extinction events on the Earth. And paleontologists and astronomers have been working on trying to figure that out. Does it actually happen? We don't know. The data are not very impressive. It looks like the correlation is not good, but there might be some examples of that actually happening. So our Milky Way is surrounded by dwarf galaxies. I mentioned the Milky Way gobbling up dwarf galaxies. The bottom part of this image is dominated by the Small Magellanic Cloud, which is about 210,000 light years away. The big glob in the upper left is the globular cluster 47 Tucanae, which is only a little bit smaller than Omega Centauri. It too must be the core, remnant core of a galaxy that got gobbled up by the Milky Way. It's only about 15,000 light years away, very much closer than the Small Magellanic Cloud. And in the lower left, the glob there is the globular cluster NGC 362, which is kind of peculiar. NGC 362 is not as old as most globular clusters, probably no more than 11 billion years old, where most globular clusters are like 12 or 13 billion years old. So if we look at the Small Magellanic Cloud, one thing we see, here's this small open cluster, NGC 290, and I put it here because here you can see the colors of the stars very nicely. your eye has a hard time being triggered by color if you go out in the night sky and just look up at the sky. Stars mostly look pretty much the same color because your eye doesn't respond that well. You look at Betelgeuse and it's pretty obviously red. But in an image like this, and if you're doing photography of stars, if you take the camera a little bit out of focus and spread the light out, then you can see the color differences even better. But here you can see the difference between the red stars, mostly probably red giants, not red dwarfs, and the blue stars, because red dwarfs are very dim and they're 210,000 light years away. You probably won't see them. So here you can see the colors difference of the stars quite dramatically. But one of my favorite images I really like, I try to squeeze this into every talk I do, but it doesn't work in most talks. There's Pac-Man, gobbling up a star cluster. So the nebula is designated N90. There's two clusters that you can see clearly in this image. One is embedded in the nebula just below center, and the other one is over on the left side of the image. For some reason that I can't fathom, they are cataloged as parts of the same cluster. So NGC 602A, I think, is the one on the left, and B is the one on the right. They look much different to me, and I don't know why they're cataloged that way. What's happening is that this cluster below center is very young, very hot, extremely hot, lots of ultraviolet radiation. It's the same thing that was happening at the Horsehead Nebula. The ultraviolet radiation is literally pulverizing the dust cloud and destroying nebula N90 as it's carved out a hole in it. And the cluster on the left already accomplished that task with its nascent cloud long ago. It's gone. There's no dust and gas around it. And so the cluster inside N90 is getting rid of it slowly. They're very massive stars. There are lots of very massive stars in these clusters. And another thing I really like about this image is that you can easily see and very quickly count at least a dozen background galaxies. There's a conspicuous one about to be eaten by the Pac-Man, and there are several others. If you look at this image carefully, you can see background galaxies all over the place. When I started doing things like this and we used film, which some of you young people might never have heard of before, but photographers used to use this stuff called film that you stick into a camera and some light hits the film and chemistry goes on and maybe it works and maybe it doesn't. You'd be lucky if you got any background galaxies using film. If you got one, you'd show it off to everybody, see, I got one, ha ha ha. But with the modern digital detectors, you just point it in like the Hubble deep field. You point the telescope at some boring, dark, empty piece of sky and 10,000 galaxies crop up. You never do that with film. So it's a really interesting image. I really like this. So our Milky Way is a galaxy in the local group of galaxies. It has an environment. And on the lower right in this chart, you see M31, the Andromeda Galaxy, and up left of center is the Milky Way. Our local group of maybe 100 galaxies or so is dominated by the Milky Way and the Andromeda Galaxy, which are both roughly the same size. There's a constant tug of war between them. Some paper will say that Andromeda is bigger, and then another paper will say Milky Way is bigger. And yeah, they're about the same size, pretty much. And all the other galaxies in the local group are like a couple of % or less of the mass of the Milky Way and M31. So we are the big galaxies in the group. So I told you the sun was bigger than 95% of the stars around. So you don't need to worry about coming from little star, average star. We come from big star. We're in a big galaxy, so we're big there too. And remember that the Earth is the biggest of the tiny planets in the solar system. So we come from the biggest little planet, big star, big galaxy. We're doing fine. We don't need to worry about that. So here's an image of M31. The oblong fuzzy object bottom center is, I think it's NGC 110. I'm not sure I remember the number quite. It's a satellite galaxy going around M31. And then above M31, almost touching it, is another glob that is M32, a dwarf galaxy that's actually on the other side. Now here you can see what I was talking about before, and I mentioned the color gradient in the image of stars in the Milky Way. Notice that the center of the galaxy, and these are true colors really, they're brightened up a little bit for your eyeball, but they're basically true colors. The central stars have a very yellowish tinge to them. Astronomically speaking, they're more red. That dominates the galactic bulge in the center of the galaxy, and the blue stars are in the spiral arms. And if you look over on the left side of the image, you can see the blue stars, a dark lane, and then yellow stars. There's a sharp demarcation between them. You can see it clearly in the image. And this is typical of spiral galaxies. You'll find the blue stars, the young stars on the leading edge of the spiral arms, and the older stars behind them and in the cores of the galaxies. And we're seeing M31 at kind of a shallow angle. M31 is heading this way, and in about 3.8 billion years, Andromeda and the Milky Way will collide. And that's probably a little bit before, but roughly the same time that the sun becomes a red giant star. So if you're around in 3.84 billion years, it's going to be a honey of a show around here. The sun's going to become a red giant in a planetary nebula over there, and M31 is going to bash into us over there. It's going to be really exciting, not on the Earth because it'll be gone, but hide out on the moons of Jupiter and drink a mint julep or something and watch the fireworks. It's really going to be impressive. So what happens when galaxies bash into each other? Well, I'm going to show you a movie that models the collision between M31 and the Milky Way. It's going to be a time-lapse movie that will show you 105 million years of real of galaxy collision time in real time-lapse time. So here we go. There's the Milky Way spinning around, and we're counting off the billions of years in the lower right. Now, during the course of this movie, the camera does some panning, and so it's not all just the galaxies moving around. The camera's panning. M31, the Milky Way, and M33. You'll see that M33 is where you really want to be because you can watch everything happen from a safe distance. So we will collide at an angle and kerwham. Now you notice they pass through each other, and this takes a billion years, maybe 1.5 billion years for them to pass through and then come back together again. And then they pass through a second time before they finally settle down and form a giant elliptical galaxy. And you notice in the simulation how many stars went flinging off into the universe. In any cluster of galaxies, our local group included, there are a lot of stars that are not in a galaxy. They're floating around out there in the cluster because of galaxy mergers flinging the stars out. When galaxies collide, the stars are too far apart. They almost never will collide with each other. It's not going to happen. But they will get close enough to do the gravitational slingshot thing, and that's why you saw streams of stars flowing out as the galaxies collided. While the stars won't collide, those great big huge clouds of dust and gas will collide, and we can see that. Here is the well known as the antenna galaxies. They are in collision. The two bright yellow spots, one on the right, in the rightmost image, one on the right and one on the left, are the centers of the two galaxies. So you can distinguish the two galaxies from each other. Their centers have not merged yet. They're in the process of colliding. And all those bright blue knots are star formation triggered by the collisions of these clouds as the galaxies collide. And that's typically what you expect. You expect lots and lots of fast star formation as galaxies bash into each other. And you can see the streams of stars that are on the black and white image on the left that you saw, for instance, in the movie of the Milky Way and Andromeda colliding. You saw streams of stars flung out. Well, we see that. We see the streams of stars flung out by the galaxy collisions. And somebody thinks they look like bug antennae, which is why they're called the antenna galaxies. And there are lots of examples of galaxies bashing into each other. So here's a galaxy called M74, the 74th object on the list of things Charles Messier never wanted to see again for the rest of the life. He hated them. But now it's the only thing he's famous for is the list of things that he hated to look at. And they're the most studied objects. And we bow to Charles Messier for the list of things that he despised. But you got to be famous for something. This is a great example of what we call a grand design spiral galaxy with nice sweeping spiral arms. And here again you notice the spiral arm stars are blue, the central core stars are yellow, and they tend to mix up around the dust lane that separates the yellowish from the bluish stars in the spiral galaxy. And as you might guess from the twist of the arms, the galaxy is indeed rotating clockwise. So if the spiral arms are bent this way, they're rotating that way. In almost all cases, that's the direction spiral arms are moving. There are a few examples of spiral galaxies rotating backwards, and nobody really understands that, but there you have it. And this one has a nice, tight center to it. The red spots are star formation regions like M42, except they're much, much bigger, and that's mostly hydrogen alpha emission that gives it the red color. So here, the spiral arms are wound up all the way to the center. But if you remember, the image of the Milky Way showed us a barred spiral, and I had another image that I forgot to mention in the upper corner of a galaxy, UGC galaxy, that looks like the Milky Way that I put in there just to show you. And so the Milky Way has a little bar. But here is an example of a very conspicuous gigantic bar. This is a really barred spiral galaxy. There's no doubt about this one having a bar in the middle, one big bar and two sweeping arms, NGC 1300. It's about the same size as the Milky Way, maybe 110,000 light years across, maybe a little bit bigger. 69 million light years away. That means it took the light 69 million years to get here. So if you build your scale model of the solar system, you're going to have to go 69 million miles to this galaxy on your scale model. And remember that Andromeda galaxy is 2.5 million light years away. So you'd have to go 2.5 million miles on your scale model to find the Andromeda galaxy. That's 10 times the distance from the Earth to the Moon. So space is really empty. Now, in the movie, when the galaxies collided, the result was what we call a giant elliptical galaxy. And here's a good example of one, M87 in the Virgo cluster. If you're outside and looking at the great big mural, the largest astronomical mural in the world, the Virgo cluster of galaxies is there in that mural, and you can see M87 on the wall of Griffith Observatory out there, and we've got it right here. So it's a great big galaxy, much bigger than the Milky Way, probably over twice as massive. We have maybe a couple of hundred globular clusters around the Milky Way. We've cataloged 12,000 around M87. And you can see them in this image. They might be a little hard to see in the projection, but in close to the galaxy, there are a lot of really dim dots that are hard to see. But if you look close at the image, you'll see them. And then as you go out towards the edges of the image, those dots go away. And those are the globular clusters. So this galaxy, like the Milky Way, has a supermassive black hole in the center. But while the supermassive black hole in the Milky Way is maybe 4 million solar masses, it's like a few billion solar masses for the one in M87. It's very, very big. And a few years ago, in 2016, I think, I forget the exact, 2017 maybe, the images were released, or the first image of the M87 black hole from the Event Horizon telescope. And so here are the images that were released, first for the M87 black hole and a year later for the Milky Way Sagittarius A star black hole. It's labeled as an image of the black hole, and that's not strictly speaking true, because if you think about it from it, space is black, black holes are black, everything's black. You point a camera and take a picture of everything black, you see black, and there's nothing there. Right? So you can't make an image of a black hole, but you can make an image of the light that orbits around the black hole. And yes, light will orbit around a black hole. The photons will go into orbit, but it's not stable, and they will either fall into the black hole or they will fling out. So no matter what direction you look at a black hole from, you're going to see a ring of light around it. And that ring will be asymmetric depending on the properties of the black hole and the tilt angle and all that good stuff. And so that's what you're seeing in these images. You're seeing what's called the photon ring around the black hole. And you'll notice that the M87 black hole on the left, the inner ring, edge of the ring of light is marked Voyager 1. So it's about 160 astronomical units from the center out to there. And that's roughly the size of the actual black hole. The event horizon of the black hole is just inside the photon ring. So a black hole that massive is really, really big and would swallow our entire solar system and be gone. But if you notice the Sagittarius A star black hole, our own galaxy, is the photon ring is about the size of Mercury's orbit around the sun, and that is about the size of the blue supergiant Rigel in the constellation of Orion. And the black hole is going to be inside the inner diameter of that ring. So the black hole is not going to be all that big. The whole photon ring and everything will be the size of Rigel. And so in our sky, it would be about this big. But unlike what they did in the movie Interstellar, you actually don't want to be that close to a black hole. That's not how you save a planet. It doesn't work. You really don't want to do that. But if you were, you'd see a great photon ring, then you get sucked into the black hole. So astronomers don't necessarily know everything about everything they see. And here is a perfect ring galaxy. Now, there are examples of ring galaxies out there, but this one is pristine. It's amazingly perfect, called Hoag's object, 600 million light years away, so it's quite a ways out. You can see the yellow core of the galaxy. The blue stars that would be in spiral arms are in a nice ring, and there's nothing in between except another ring galaxy off in the background. That's the one with an SDSS, Sloan Digital Sky Survey designation. So we know how to make a galaxy like that in principle. You have a spiral galaxy like the Milky Way, big, and a little bullet galaxy comes running through and crashes perpendicular right smack into the middle of the Milky Way type galaxy. And you do that, you're going to get a galaxy like this. But you're also going to get junk left over. You're going to get a nice ring galaxy and junk. This image has no junk. It just has the ring galaxy. So where is the other galaxy? Good question. Nobody knows. We have a hard time figuring out how old it is, but if it's maybe a few billion years old, you can argue that the remnants of the little galaxy might have dispersed by now and we wouldn't expect to see them. But it is something of mystery. It takes a perfect collision, and we would like to see the remnants of the colliding galaxy, and we don't. So how did this galaxy come along? Nobody's absolutely sure. But it's a really nice image. Now, when I was a kid growing up in the 50s and 60s, say the 50s certainly, this galaxy, M82, was cataloged as an exploding galaxy. And then the 70s came along and astronomers got sophisticated and realized galaxies don't blow up, must be something else going on. And then the 90s came along and the Hubble Space Telescope, and we went back to exploding galaxy. Yeah, it's blowing up. And so here's what's happening. M82 is a companion to M81, and some few 100 million years ago, they bashed into each other and passed through each other, just like in the model collision you saw for Milky Way and M31. M81 is big, and so it kind of held itself together and had a burst of star formation. But M82 is much smaller, and it had a big burst of star formation, and all those stars formed at about the same mass, about the same time, which means they all blow up into supernova explosions at the same time. And so what you have is all these overlapping supernova shock waves sweeping through the galaxy and blowing all the dust and gas out of it. So the oblong blue image that runs diagonally from lower left to upper right, more or less, that background image, that's a Hubble Space Telescope image of the stars in M82. The red is a Spitzer Space Telescope image of the warm dust and gas being blown out of the galaxy by all these supernova shock waves, and the blue-white that you can see stretching, say, from lower right to upper left, that is super hot gas imaged by the Chandra X-ray telescope. And all that was combined to make the 16th anniversary image to celebrate the birthday of the Hubble Space Telescope in 2006. So yes, galaxies do blow up. This is an exploding galaxy. There is the biggest galaxy known. It's sort of an elliptical galaxy. You can see it in the digital sky survey plates on the right in optical light, IC 1101. The galaxy is about 2,800,000 light years across, which is larger than the 2,500,000 light years that separates the Milky Way from M31. It is gigantic. And that's halo stars. The core of the galaxy is, only about 400,000 light years across. So it's very, very big. These two images are the same scale. The image on the right is the digital sky survey plates. The image on the left is from the Chandra X-ray telescope and shows X-ray emission. Now, one of the problems understanding dark matter, for instance, is that we can see galaxies in a cluster don't move the way they should if what we see is all there is. So there must be extra mass to make the galaxies move that way. And another branch of evidence along the same lines is this hot gas. It's not going anywhere. It's millions of kelvins. It should fly off into space. It's not going anywhere. It's trapped in the gravitational well of that cluster, and there's way not enough gravity from the material that we can see to do that. So either we've got the law of gravity wrong, or we've got need dark matter. Dark matter is the better solution because nobody's ever been able to make a modified gravity model actually work. Maybe someday they will, but for the time being, that hasn't happened. Whereas the assumption that there's dark matter pretty much solves all your problems. You just don't know what it is. You call it dark matter and it's a placeholder, and maybe we'll never figure out what it is. But it's the simplest solution to the problem of something like this. But this is the largest galaxy we know, dwarfs. It's bigger than our whole local group of galaxy cluster, all by its lonesome self. Meanwhile, thanks to the James Webb Space Telescope, here is the most distant galaxy currently known. A spectroscopically confirmed redshift, 13.2, puts this galaxy 325 million years after the Big Bang. This is the kind of thing which, if you troll the internet, you will find all kinds of videos and web pages telling you that Big Bang cosmology is doomed. The James Webb Space Telescope has proven that it's all wrong. You pass those websites up. No, it doesn't. What it does prove is that we don't know how galaxies are formed, which is not very dramatic because we already know that we don't know how galaxies are formed, so that's not news. But we thought galaxies should take longer than this to form. It's a small galaxy. It's only a few billion solar, about 63 billion solar masses, but it's a galaxy, and it's only 325 million years after the Bang. What this really is job security for the people whose job it is to figure out how you form galaxies, because all the old ways, they're out. Now you have to figure out a new way to do it fast. So we like this kind of thing in the astronomy business because we have a job, right? So, and something else I'm going to point out, I have given you a light travel time distance, 13.395 billion years. In a universe that's, 13.7, 13.8 billion years old. Every distance you ever see in any book, any web page, any publication, it's going to be the light travel time distance always, which is completely fake. That is not the distance. It's not even an approximation of the distance between here and that object. It is, in fact, a measure of time. It's how long it took the light to get from there to you. It took 13.395 billion years for the light to make the journey from that thing to us. It's a measure of time, not distance. If you freeze the expansion of the universe right now, if you have your Harry Potter wand and you cast some magic spell, whatever it is that takes quite a spell to freeze the expansion of the universe. But if you can do it, and then get out your yardstick and pace off the distance. Now I'm going to pace off camera. Goodbye. You pace off the distance between you and the thing, and you're going to pace off 33.382 billion light years worth of miles, or feet, or inches, or whatever you're using, because during that 13.395 billion years that light was heading this way, the universe was expanding. And it can do a lot of expanding in 13 billion years. So by the time the light gets to us, the distance is very much different than it was when the light left, because the universe is expanding. And so you need to do what's called the proper distance. And you can calculate that if you look for Ned Wright is a professor at the UCLA, and he has a web page called Ned Wright's Introduction to Cosmology Tutorial, something like that. Look for him. And he has a cosmology calculator on his tutorial page. You can go to his cosmology calculator and put in your favorite numbers, and you can figure out all these distances and travel times and all that good stuff. So we have gone all the way out as far as you can go to the most distant galaxy that we know. Beyond that, we only have the cosmic microwave background, which isn't really far away because it's right here and doesn't really tell you much. So we've gone as far into the universe as we can. But we must remember, in all those incredible trillions of cubic light years that make up the universe, this is where you are. And in fact, you're right down there at the, north of Baja, California. And this is the only place I know of where we can hang out. And as Dorothy found out from The Wizard of Oz, there is no place like home. So take care of it. That's my political message for the day. And with that, I'm done. Thank you. And I will answer questions until somebody decides that we should stop because of time. Let me take a question or two in here first, because
If you guys have a
people are
question
actually in
on
front of
Zoom,
me,
type it
and
in
then we'll
the
let the
chat.
Zoomies ask some questions. So who's got a question? Somebody. Yeah, we need. Well, the microphone wasn't working. Evan, do you know if the microphone's working?
The mic is working now.
Oh, okay.
So there's a question on Zoom. I pasted it put it up on the screen.
Okay. And so nobody can hear you on Zoom unless you talk into the microphone. So you have to talk into it and ask your question so they'll know we're not trying to have some secret meeting in here without them, right? Yeah, I see.
Check 1, 2.
Yeah.
Where's it at?
Go ahead.
Hey Tim, this is
Yeah.
Jeremiah here.
Yeah.
I like that really beautiful, perfect spiral galaxy we saw. And we saw the location of the Earth in our Milky Way spiral galaxy.
Yeah.
Do we ever look at other spiral galaxies that are similar to ours and look at the location that our Earth and our solar system is in relation to its center and to the outside arms of the spiral galaxies? Are there similar galaxies and other spiral galaxies that are like ours?
Well, there are certainly many spiral galaxies that are like ours. I will make you all very dizzy now. And so in the upper right is the image of UGC 12158, which looks a lot like the Milky Way. So yes, there are galaxies that look like the Milky Way. We certainly do look at Milky Way type galaxies. I don't think anybody bothers to look specifically at Earth's distance in that galaxy. We look at the whole galaxy. We look for anything that's interesting that we can see, but I don't know that anybody concentrates on that particular point.
Okay, over here.
Hi, it's Victoria. Hi, Tim.
Yeah.
Thank you. I have a lot of questions, but I will save most of them for Garvey. But one
Okay.
question I have tonight is, you mentioned that the stars are less dense towards the center of the galaxy and denser around the arms. And I don't think you got much into why. And I'm just curious if it has anything to do with like their age and how close they get to maybe our black hole.
It's not that the stars are less dense. It's that they're smaller. They're probably more, well, I don't know if they're more densely packed in space in the core of a spiral than they are in the arms. They're lower mass and they're older. So the core of the galaxy forms first and for some reason loses a lot of its gas and dust. So there's very little star formation in the core of a spiral galaxy. And the halo stars are also small. But in the spiral arms of the galaxy, that's where most of the dust and gas is that you can make stars. And so the more massive stars are found in the spiral arms of a spiral galaxy, and the less massive stars are found in the central bulge and also in the halo that surrounds the galaxy. And of course, the more massive stars are also younger. They live faster lifetimes, very much faster lifetimes, and they're very much more massive and very much hotter. Does that answer your question? Is that
She's,
okay?
she meant mass, not gravity, right?
It
What's
was
that?
mass, not density. Yeah. So, and so I will read a question here from Zoom. It says, well, I was going to read it, and then it went. Einstein's theory of relativity suggests that for an object falling into a black hole, the moment would be over in an instant for the object, but the space-time dilation would make the object freeze on the event horizon for the black hole when observed from afar. Does this mean when we observe the event horizon ring on the black hole images of M87, the Milky Way, the light we see represents light from everything that has ever fallen into the black hole? Yes, that's basically correct. If you're watching a black hole from a distance and you watch something fall in, you will never see it cross the event horizon because the time dilation becomes infinite from your point of view as you reach the event horizon, so you never see it. But that's what's called a coordinate time. It's not a real time, it's a fake time. It's a coordinate time. The real time is the time whoever unfortunate person is falling into the black hole sees on a clock they're taking with them. And they will fall right through the black hole and event horizon and say, oh boy, I'm in a black hole. Oops, it's a little late now to worry about it. And so that light comes from maybe a accretion disk, whatever is going down in there. It's not, the light doesn't come out from inside the black hole, you understand, because that nothing can come out of the black hole. But the light, yes, comes from all the stuff around the black hole and forms a shell of photons around the black hole that are orbiting in all manner of random circular orbits. Those photons can fall into the black hole or they can come out. And when they come out, they will come out so that whatever direction you're looking at it, you will see a ring of light, just like we saw in the black hole images. And I should actually put those images up here, there. And so this...
Mike Gardner raised his hand.
Yeah.
Mike?
Yeah, thank you. Great talk, Tim. I'm curious, if you're in the middle of, say, Omega Centauri, what kind of image would you see? How close would those stars be together? And in fact, could you see the Milky Way?
So if you draw a box around the sun, put the sun at the center of the box, and make the box 3 light years on a side, there's one and only one star in that box, and that's us. You do that at the core of Omega Centauri, and as I recall, the number was something like 5,000 stars in that box. And so, yeah, you would never have what we call a dark nighttime sky. It'd be like moonlight or something. You just couldn't do it because there's so many stars packed together. Okay, how about a question from inside the room? Who's got the microphone?
Here.
Okay, go
Annie.
for it.
I read that comet C 2021 will be visible early morning in Europe. Will it be visible here?
I am not familiar with that comet, so I can't tell you when, but there must be at least one comet observer. Dave Nakamoto is on Zoom, and he does comets for a living practically. Do you know that comet, Dave? Do you know when it's going to be visible?
Muting. There I go. I've never heard of that comet, but to answer her question, it wouldn't be just visible from Europe. Any comet that is visible, let's say they say it's visible from Europe in the morning time sky. Well, it's visible from any portion of the Earth in their morning time sky. Remember, comets are not tied to the Earth. They're out there in the solar system. So if Europe sees it in the morning, then you wind the clock. I forgot which way you wind the clock. And then Asia will see it in their morning, same day. And then Hawaii will see it in their morning, same day. I think I'm going the wrong direction there, but anyway. But if it's visible anywhere on the Earth during a particular like morning or evening, it's going to be visible from any other portion of the Earth within a reason that same morning or that same evening. There's no geographical reason why it shouldn't, unless, of course, the silly comet is in the southern portion of the sky, in which case Europe and nobody else in the northern hemisphere is going to get a good look at it. So you might as well go to Australia to get a good look. That's the only reason you wouldn't see a comet, is basically north-south, not morning or evening. I hope that answered your question. But as for that particular comet, I never heard of it before.
Well, now you've got your homework set up for you. Look it up.
Annie made it up. Just kidding. We have another one here when you're ready. One right over here.
Okay.
Tim, that was an awesome talk. I really enjoyed it. I was curious, you mentioned a few times about how the stars at the center of galaxies bulge. If I was understanding you correctly, above the galactic plane, what causes those center stars to bulge?
So if you look at the edge-on spiral here, you notice the bulge.
Tim, are you showing your screen?
The natural shape of anything under gravity is going to be a sphere. It's the minimum energy configuration. So if you just turn something loose and let it have gravity, it will collapse into a sphere. And that's what's happening to the core, because the core isn't rotating very fast. The outer part of the galaxy is rotating relatively fast and is forced to flatten out by angular momentum conservation. So it's basically a momentum problem. The bulge is just too small to flatten out, but when you get far enough away from it, you get the spiral arms and the flat part. And I think I'm being thrown off the stage. So thank you.
Thank you, Tim.
Yeah. Go for it. Now I have to turn off my mic.
Okay, use this one here.
Okay. All right. Before we get started, thank you again, Tim, for that fantastic talk. We definitely appreciate it. I absolutely loved it. All right. So I want to know if there are any new members here tonight or any guests. Raise your hand or stand up. You wanna?
My name is Eric Liliestrand. I was a member maybe 25 years ago, and then gradually got out of the field. And you're gonna have to say it again on the microphone. Oh dear, I'm sorry, I forgot. How soon we forget. My name is Eric Liliestrand. I'm back after, well, like I said, I was a member maybe 25 years ago. Around that time, I purchased some property in Joshua Tree, and my jaw dropped in a way that it hadn't since I was a kid. And basically had children and got busy and drifted away from the hobby, and now I'm back, bought a new telescope, and here I am.
Hope it wasn't recently, so we don't have bad weather this Saturday. Next, who else? That's good for me.
Well, thank you. My name is Dale Fields. I'm a professor of astronomy at one of the local colleges, Los Angeles Pierce College. And this is over in the western part of the valley. And this is LAS members have been so helpful with Nady and this is, David and Phil. This is towards helping us set up and do some of our events. And I'm this is wanting to come along and see this. And hopefully I will this has become a member in the future.
Anybody else out here? New? Anybody on Zoom that's new? By the way, does everybody have a ticket for the raffle here? Everyone has one? Okay.
Okay, I just posted the link on in the chat for the people for the raffle.
Committee reports. Yeah. All right. So now on to the committee reports. For disclose, Mount Wilson dates have been released, so please reach out to Daryl for spots and payment. Keith and the team over at Garvey have made great strides with the cleanup, so a big thanks to everyone involved with that. Round of applause for Garvey. Thank you again. Lockwood Committee. This is a big deal for this one. They plan to clear code violations has been submitted to Ventura County. We're waiting to hear back from them. The second visioning session to inform master plan scheduled for 8 p.m. April 23rd. So stay tuned for our email announcement via the Zoom link that will be sent out. And that's it for the committee reports. Other than, website committee, we are having the astrophotography contest, like I mentioned earlier. So look out for that email announcement as well and get your pictures ready. All right, so now for the door prize drawing.
For those of you on Zoom, if you haven't submitted your name in the raffle, do so now. I'm going to close it out in about 30 seconds.
Okay. Yeah, let's start here. I know, I saw, it was so cool. I can't pick, they're stuck to each other. Okay, here you go.
Okay, here we go. First, our number is, they're all starting with 8334. The last number is 816. We got a winner. What did we get? You want a green laser. They're here. So, does you want to get them now or? Okay, you want to come down and get it? Wait, is that Keith? It's about time you won something. Holy mackerel. Way to go. Also, Keith is the guy responsible, if you don't know, he's also one of our board members, but responsible for really cleaning up Garvey. Give him a big hand. He's been working his tail off. And a lot of stuff at Lockwood he does too as well. Thank you so much. And it's about time you get a laser. Yeah. All right.
Oh, okay, next one. There you go.
Okay, next number is, ladies and gentlemen, get your tickets out. Here we go. The last numbers are 4820. Wow. Yeah, is that? Annie Gross, what you got?
Binoculars. You won binoculars. I know, right? Here you go. They're binoculars. They're Celestron binoculars. 15 by 70. Yeah. 15 by 70.
She got, Annie just won 17 by 50 Celestron binoculars. Okay, now the Zoom drawing, go ahead.
Okay, hang on 1 second. Let me just. All right, here we go. Steve Cooperman.
All right, Steve
Yeah,
Cooperman just won an item from the LAS store.
Yay, thank you.
Want to do one more in Zoom?
Mm-hmm.
Okay.
We can do 2 more.
Chris B.
Oh,
Just won an eclipse book for the upcoming eclipse. One more. We're doing one more.
One more in Zoom?
Yep.
Okay, all right, hang on. Soren Thay.
Hey, that's me.
that's who?
Anza.
Oh, he won Observer Sky Atlas.
Ooh.
It's really cool and very much appropriate for this talk today. Okay, so we have more here in-house.
And the winning number is, it's 8334. The last numbers are, let's see, 8334 is 824. 4824. Your mother? No, you win. Congratulations. No, you win. Sorry. And what did your mother win? She's cracking up over here. Come on.
Crap. You want a red flashlight bulb. What? Oh, I know we have so many of them at home. Yeah, I'll give to someone else. Here, hold on. Here, do that.
She's so generous. She just gave it away. So the number's going to be 833 4817. Right over here. Congratulations. You won a red flashlight. Go over and get it. Okay. And this winning number is 833. The last numbers are 4821. 4821. Who got it? Dr. Fields from Pierce College. All right.
Yeah, one more
You
in
won a
Zoom.
Keurig. For those cold nights as an astronomer.
One more in Zoom.
So we get some coffee and some hot chocolate when we come over to Pierce College, right? All right.
Oh, okay. Yeah, I can do that. All right, let's do one more on Zoom.
Okay. Alexandra.
Oh.
Hi, everyone.
Won a
Thank
map
you.
of the moon.
What was
She
that?
won a map of the moon.
And what did Chris
Alright,
B
so-
win? What did Chris B win?
Crispy won the Eclipse book.
Okay.
Of nine-
Okay.
It's a really good book. It's awesome. It tells you everything about eclipses you could possibly want to know historically wise.
Okay.
Yep, we're good. We're good, Tim. So, meeting is adjourned. We will stop this. Thank you, everyone, for tonight, and thank you again for our speaker and for our guests. Thank you.
Don't forget our star party is here this coming Saturday. We should have pretty decent weather, 2:30 till 9:30 at night. And don't forget, we also have outreaches go online. Check those out. And thanks to Evan Renteria for doing all that stuff.
Check out our LAS online store. Yeah. All right.